You can hear me fine, right? Like, okay, everyone online can hear me fine, correct? Just thumbs up. Okay, thank you. Okay, so we will get started. So for question 3, it states that a new transmembrane protein is discovered which contains a 26 residue long alpha helix. How many full turns are there in this alpha helix? So the stuff that I have starred throughout these problems in pencil, you should probably know that most likely. Like they're either constant or just like a little bit of concepts that you guys should know. So what I have starred here is an alpha helix has 3.6 residues per full turns. So we know that we have 26 residues here. That's how long our alpha helix is. And so we divide the 3.6 amino acids, which is also known as residues per turn, and you get about 7 full turns for 3A. So just know that on average it's 3.6 residues per full turns. That's one of your constants you're supposed to know. Okay. I'll wait a little. Do you guys have any questions on that so far? Any questions? You're good, okay. Okay, I will move on to the next question. So, how many hydrogen bonding interactions would be there in this alpha helix? So we have to know that alpha helices have n-4 hydrogen bonds, where n is the number of residues. So they give us 26 residues up here. And so we're going to subtract the 4, and it's going to be equal to 22 hydrogen bonding interactions. And then for 3C, let me like move this. Okay, so what is the length of the helix in angstroms in the direction of the helix axis? So you have to know that the rise over residue of an alpha helix is equal to 1.5 angstroms per residue. So the length of the alpha helix is going to be equal to 26 residues times 1.5 angstroms per residue, which is equal to 39 angstroms. Just gonna move on if no one has questions. Okay. For D, it says if the lipid bilayer is 36 angstroms thick, is this alpha helix long enough to span the bilayer? Calculate and explain. So they give us 36 angstroms. You divide the 1.5 angstroms per residue, which you're supposed to know, it's a constant, and you get 24 residues needed to span the bilayer. So since our alpha helix residue that was given in this problem 3 before, it said that our alpha helix is 26 residues long, we will have enough residues to span the bilayer because it is longer than the 24 residues that are required to span the bilayer. We have calculated here. Does anyone have any questions? You guys, okay. It's pretty straightforward, question 3. But then question 4 is a little bit more calculation. So the following rate constants have been determined for a Michaelis-Menten enzyme. So K1 is equal to 3.5 times 10 to the 8th, M-1 to S-1, which is just molar in seconds. And then K-1 is equal to 3 times 10 to the 7th, S-1, and K2 is equal to 7 times 10 to the 4th, S to the power of -1. So calculate the Ks and Km for this enzyme. So I don't know if you guys have learned this yet in class, but Ks and Km are essentially the same. But the Ks here is just, I kind of wrote this little last minute because I saw it on one of your slides. So it's like K-1 over K1 is this. So the Ks is basically like part of this little equation. So this is what it is. So this is the K negative 1 because it's going reverse. This is the K1 because you're going forward. It's a forward reaction. So for Km, on the other hand, it's going to be K negative 1 plus K2 over K1. So you have to add this to this and then divide it by this thing. So they give us some of the numbers. So for A, it says calculate Ks and Km for this enzyme. So Ks is equal to K negative 1 over K1, which is going to be 3 times 10 to the 7th seconds to the power of negative 1 over 3.5 times 10 to the 8th molars times seconds to the power of negative 1. So you get for Ks equals to 0.086 molars. And then for the Km, it's going to be equal to K negative 1 plus K2 over K1. So Km equals to 3 times 10 to the 7th, 1 over seconds plus 7 times 10 to the 4th, 1 over seconds divided by 3.5 times 10 to the 8th molars times second inverse, like 1 over that, and it's equal to the same. It's equal to 0.086 molar. I know it's a little confusing. You've seen this equation, right, before? Seriously? Okay. Okay, you probably will get to it then. Okay. So I'm going to move on to 4b. Okay. So does the substrate binding approach equilibrium or the steady state? Explain why. So this system will approach rapid equilibrium since K2, our value that we got, or our value that we have here, is way less than K1, which is 3.5 times 10 to the 8th here. And then it's also, the K2 value is less than K to the negative 1. So this makes the K2 the rate limiting. And also one thing to note, I don't believe you guys have gone over this yet in class, but you probably will. So when the Ks is equal to Km, like we have above here for 4a, then that means you're going to be also approaching rapid equilibrium as well.
Ks and Km aren't always equal.
They are.
They're so for A, you calculated them 2 different ways, but they'll always end up being equal.
Oh no, like Ks can be Km, but like Ks is basically just part of this equation, so it's not always equal. If that would make sense. Like Ks can be Km though, if that makes sense.
So you should do both.
Yes, yes.
Solve them separately.
Yes. Okay. Okay, I'm gonna move on to 4c. I believe if no one has questions. Okay, so in a 500 microliter reaction containing 4 picomoles of the enzyme and saturating levels of substrate, what is the Vmax for the enzyme? Assume 1 active site per enzyme molecule. So we're going to do 4 picomoles, and it's equal to 4 times 10 to the negative 12th moles, and then 500 microliters, which is equal to 500 times 10 to the negative 6 liters. And then this is going to be our concentration, how you figure it out. So you just divide these two numbers, and you get 8 times 10 to the negative 9th molar enzyme concentration. And since we're trying to figure out the Vmax, what we're going to do is, okay, so we're going to do K2 times E, the enzyme, initial enzyme concentration, and it's going to be K2 equals to 7 times 10 to the 4th seconds inverse. So you're going to multiply this, you're going to plug it into the Vmax equation, and multiply it by the concentration, and it equals to 5.6 times 10 to the negative 4th m over s Vmax. So just know, like as a hint, like Vmax is basically velocity. As you guys know, like the maximum velocity, and velocities units are meters over seconds or like molars over seconds. In this case, in the Nicholas-Menten, they're always going to be molar over second, or it could be like millimolar over second. But just like plug and chug here to get to the Vmax. Does that make sense? I'm going to move on if no one has questions. Okay, so for 4D, what substrate concentration would be needed for the reaction in 4C to achieve half maximal velocity? So you guys, and justify answer mathematically, you guys have to know that the substrate concentration at the 1/2 Vmax is equal to the Km. You can see this through the graph also. I just don't have it drawn because we didn't really, we're not supposed to be using a graph for this problem, but when you get into like when they teach you in class, they probably will show you the graph and the Km marked, and the Km is going to be on the x-axis because it is a substrate value essentially. It's just 1 point on the x-axis. Okay, so the S, which is the substrate concentration, equals to Km, which is equal to 2.09 times 10 to the -4th molar. So we're going to do an equation derivation. So this is a Nicholas-Menten equation. So it is V naught equals to V max times S divided by S plus Km. So this is not the Nicholas-Menten equation. This is just basically the Y value of when Km is going to be equal to the Vmax. So basically at this point, when Vmax is divided by 2, like I said before, that's when its X value will be Km. So what we're going to do is we're going to make these two equations equal to each other, V naught, these two V naught equations. So it's going to be Vmax divided by 2 equals to Vmax times S over S plus Km. So this is my Nicholas-Menten, and this is this one. So I bring the Vmax to the side, I divide it, and it cancels out, and then I bring this here. So I multiply it by 2, and then I bring this here at the same time. And so it's S plus Km equals to 2S, and then Km equals to 2S minus S. So because of this, the Km, when it equals to S, the Vmax divided by 2, it will equal to Vmax divided by 2. I know this is like kind of confusing because it has a lot to do with algebra mainly. But overall, just know that when Vmax divided by 2, 1/2 of Vmax is going to be having an X value of Km. I will give you guys time to write it, the question. Any questions? Can't see anyone. Just talk out loud because I can't see you guys online. You guys are writing in the chat box. Okay, so I'm gonna move on. Okay, so for 4E, what is the efficiency of this enzyme? Would this enzyme be considered a perfect enzyme? Explain. So the efficiency is going to be equal to Kcat over Km. So this is an equation you have to know, catalytic efficiency. And so it's going to be Kcat, the units are like 1 over S, or S to the -1 power. And so in this case, Kcat equals to K2. And we know that our K2 has been given. Our K2 has been given right here, 7 times 10 to the 4th, S -1. So we're going to use that, and we're going to divide the 2.09 times 10 to the -4th molar, which we figured out in the previous problem. And it's going to be equal to 3.35 times 10 to the 8th molar times seconds inverse. So this is just basically an equation you have to memorize for catalytic efficiency, and just plug in the numbers and you will get this. Remember these units for catalytic efficiency also. Okay. Because M-1 is the Km. Km is generally like molar because it's concentration, and then K2 is 1 over seconds. So I forgot to answer the actual question. It says, would this enzyme be considered a perfect enzyme, and explain? So yes, this is going to be an ideal substrate specificity or efficiency between 10 to the 8th molar times second inverse and 10 to the 9th molar times second inverse. So we get these because this number that we figured out here, the catalytic efficiency, is between these numbers. This is just like 1 times 10 to the 8th to 1 times 10 to the 9th power. I will move on. If 0.5 millimolar of an irreversible or classic non-competitive inhibitor is added before starting the reaction, what is the resulting Km for the enzyme? So I don't know if you guys have memorized the non-competitive, competitive inhibitors and uncompetitive and mixed, basically like how they change on the Lin-Weaver-Burk plot and if they bind on the active site and stuff, or allosteric. But here you just have to know that for the test overall, like how it shifts the Km and the y-intercept and stuff, the Vmax. And so if 0.5 millimolar of an irreversible or classic non-competitive inhibitor is added before starting the reaction, what is the resulting Km for the enzyme? So because the non-competitive inhibition binds away from the active site, so essentially it's not going to bind to the active site, but it's going to bind to the allosteric site, the Km will remain the same. So it's still going to be 2.09 times 10 to the negative 4th molar. So if it's like non-competitive, uncompetitive, and mixed, it's going to bind to the allosteric site. It's not going to bind to the active site. But if it's competitive inhibitor, then it's going to bind to the active site.
So if it was a competitive inhibitor, your Km would change. Like,
Yes. Oh, sorry. Also, okay, so if it's an uncompetitive inhibitor, then the Km would change. And also if it was a mixed competitive inhibitor, and also if it was a competitive inhibitor. So the competitive inhibitor, the Km would increase. For the uncompetitive inhibitor, the Km would decrease. And the mixed competitive inhibitor, it would either increase or decrease because it's mixed. And then the Vmax, so just know that, memorize that for the test, like how Vmax, whether it changes or not for each inhibitor or not. That makes sense. Does that make sense?
so like if we did have that, we would just say it goes down or goes up if we didn't.
Yes, most likely.
Right, we wouldn't have to calculate.
Yeah, you wouldn't have to calculate. You would just have to be like just memorize the Vmax and Km, how they change. Okay, I will move on if no one has questions. Okay, so for 4G, a reversible inhibitor with Ki initial equals to 10 times 10 to the negative 4th molar. It's added to the reaction, and then the observed Km remained unchanged, but the Vmax was shifted to decreased value. What type of inhibitor is this, and explain? So the same for this, like I said before, the Km will remain the same, and the Vmax, if it will decrease, then it's going to be non-competitive inhibition. So in a non-competitive inhibitor, the inhibitor binds at allosteric site, changing shape of the active site. So it's going to block the reaction from occurring because it's an inhibitor, but it's just going to bind at the allosteric site because it's not competitive. And so this decreases efficacy of enzyme Vmax, but doesn't change substrate affinity Km, since the substrate can still bind, but it didn't bind to the active site. I will move on. This is the last one, I believe. So for H, if the concentration of the inhibitor from part 4G is 4 times 10 to the negative 5th molar, which will be the resulting apparent final Km value? So we know that it's going to be the same. The Km won't change because the 2.09 times 10 to the negative 4th molar, it'll stay the same because the Km remains the same due to the non-competitive inhibition. So that is it. Do you want me to draw like a chart explaining like if the Km increases for what competitive inhibitor, non-competitive, and like the Vmax increases or decreases to make it a little more make sense to you guys? Yeah. Okay. Here, I'll wait. I'll wait a little for you guys to see 4H, and then I'll just like basically write the thing down that you have to memorize. Because it's 320. I will write on the back basically what happens if no one online has questions either. So basically, I'll write in pen. Okay, so for the inhibitors, we have competitive. The pen is like breaking. Okay, competitive inhibitor. And then we have, it looks so bad, okay. We have non-competitive, which is what we saw in our problem. Uncompetitive. And then we have mixed. So I'm just gonna like go over the basics. I'm not gonna like draw the graphs and stuff, and like how they change. But you guys can feel free to email me. They're probably gonna go over it definitely on your slides and stuff. It's gonna be shown there. So competitive inhibitor. So for the Km, remember that is the X value when there's 1/2 Vmax. Look at the Vmax. Relatively simple. So for the competitive inhibitor, the Km will increase and the Vmax will stay the same because it's binding at the active site. So, and then for this one here, and then for the non-competitive inhibitor, the Km will stay the same and the Vmax will decrease. So for these three, just know that the Vmax will always decrease because it's not binded to the active site. So it's going to decrease for this one and this one. And then for the uncompetitive inhibitor, the Km will decrease. And then for the mixed inhibitor, the Km, since it's mixed, it's going to increase or it can decrease. Does that make sense? I'll highlight them. So just know this. I know you guys haven't learned so much about like Nicholas-Menten yet, but this is like the basic kind of. Okay, does anyone have any questions? Because that is it today for class. Okay, I will stop the recording if everyone's good. I know you guys have not like fully learned this yet. You can email me if you have any questions once you get to this in class. And I think we are done. So I will stop the recording.